Okay, so good morning, all of you, in this class of condensed matter physics. And today we are going to discuss about X-ray diffraction. And in X-ray diffraction, we will be discussing about the different laws, different theories or formulations that were made to understand how the crystals, if they are, they can diffract the X-rays. So all these things we are going to discuss. But before that, let me recapitulate the previous class. In the previous class, we discussed about the lattice planes and so, for example, in this picture, we can see a BCC structure, and there are 4 unit cells connected of the BCC structure together, and the shaded area here shows 0, 1, 0 family of planes. It should not be inside the small bracket, but it should be inside the curly bracket, as it has to represent the family of planes. But here it is shown in the smaller brackets. That is not a right way. It should be inside the curly bracket. So 0, 1, 0, it represents a family of planes. And you see here, if we have this 0, 1, 0 family of planes, then it all the lattice points are not included here. For example, this would be 0, 1, 0, this would be 0, 1, 0, this would be 0, 1, 0, but the atoms which are at the center of the unit cell, they are not covered by these lattice planes. So these are not very important family of planes. But here you see, if we consider the 0, 0, 2, 0 family of lattice planes, that in that way it can cover all the lattice points. So these planes are more important in case of BCC structure. Similarly, if we consider 1, 1, 0 family of planes, then you can see that it can cover all the lattice points or all the atoms present in the crystal. So in case of BCC structure, the middle one and the last one family of planes are important because they cover all the lattice points or all the atoms present in the crystals at the lattice points. Then we discussed about the reciprocal lattice and how we define the reciprocal lattice. In a crystal lattice, there are many set of planes with different orientations and interplanar spacings. If we draw normals to the set of planes from a common origin whose lengths are equal to the reciprocal of the interplanar spacings of that particular set of planes, then end point of these normals form a lattice called reciprocal lattice. Every point of this reciprocal lattice is characteristic of a set of planes. The direction of this particular point from origin indicates about the orientation of the planes, and the distance of the point from the origin is proportional to the inverse of the interplanar spacing. This we have learned in the previous class, and we have seen how we calculate the primitive vectors of a reciprocal lattice in terms of the primitive vectors of a direct lattice. And we have also seen some properties of the reciprocal lattice, and these are the followings. First is, a reciprocal vector is normal to a particular set of planes. That is one thing we proved. And then any reciprocal lattice vector is inversely proportional to the interplanar lattice spacing of the corresponding set of planes. The third is that the volume of a reciprocal unit cell is inversely proportional to the volume of the direct unit cell. These are few properties related to reciprocal lattice that we discussed in the previous class. And we also discussed why we should study the reciprocal lattice, or what is the importance of reciprocal lattice, and it would be clear today, because I told you that when we study the X-ray diffraction, then what pattern we get after diffraction is the reciprocal, that is in the reciprocal space, or that is the Fourier transformation of the direct space or direct lattice. So Fourier, if we say Fourier transformation, or if we say reciprocal lattice, these things are the same. Today we are going to study. Today we will study about what are the conditions that should be fulfilled if we want to observe X-ray diffraction from a crystal. And we also studied about the Brillouin zones. And what is the definition of Brillouin zone? For example, you consider this figure in which different reciprocal lattice points are shown. So because it is a two-dimensional picture, so each point is represented by two indices. And while defining the reciprocal lattice, uh, we were told that every point in reciprocal space represents a particular set of planes in the direct lattice. So here 0, 1, this point represents all the 0, 1 planes which are parallel to each other. Here this point represents 1, 1, 1, 1 plane, 1, 1 lines in the direct lattice. And from this arrangement of points in the reciprocal space, we can draw, we can define the Brillouin zone. A Brillouin zone is any primitive unit cell of the reciprocal lattice, or we can say it is the Wigner seed cell of the reciprocal uh, space or reciprocal lattice. So we consider this point, which is defined as 0, 0. Then we connect all the points to this is a oblique reciprocal lattice, and we from this origin we connect all the points, and then we make the perpendicular bisector. Then we make the perpendicular bisector of the lines joining the nearest neighbors. Then the area formed by this will define our first Brillouin zone. Similarly, if from this origin, if we connect the next nearest neighbors like this, these points are the second nearest neighbor, and if we draw their perpendicular bisectors, then whatever region we will get, that region would be called as the second Brillouin zone, and so on and so forth. So this is known as the Brillouin zone, and after the scientist Leon Brillouin, and he was also one of the students of Sommerfeld. One day I told you about Sommerfeld, how great people have worked under his tutelage. Sommerfeld himself could not get Nobel Prize, but he produced several Nobel laureates. So Leon Brillouin is also famous for, besides this Brillouin zone, Brillouin theory, he is also famous for other things like WKB approximation. You might have studied in quantum mechanics. So here B is also Brillouin. And WKB approximation, you might have studied in quantum mechanics. It is to provide the solution of time-dependent Schrodinger equation. All right. So this is again the picture of different Brillouin zones, and we start with the reciprocal lattice point z is equal to 0. All k points which are closer to this point than to any other reciprocal lattice point define the first Brillouin zone. So this area represented by white square, it is the first Brillouin zone. And similarly, we can define the second Brillouin zone when we connect the when we connect the second nearest neighbor to the origin and we draw the perpendicular bisectors of the line joining the origin to the nearest neighbors, then the space that forms after joining these perpendicular bisectors, that is known as the second Brillouin zone. So this is the first Brillouin zone, and this where 2 is written, this represents the second Brillouin zone. Similarly, we can construct third Brillouin zone, fourth Brillouin zone, nth Brillouin zone we can construct. And so like this. So now a little bit more thing about Brillouin zone. The first Brillouin zone is necessarily connected. So you can see this is a complete diagram. It is a complete square. So it is whatever figure you take, the first Brillouin zone will always be complete. But here if you connect, if you see in all other Brillouin zones, they are having disconnected pieces. So one part of the Brillouin zone is second Brillouin zone is present here, the other one is here, the third one is here, the fourth one is here. But important thing is that a point on a Brillouin zone boundary. So for example, this is the boundary of first Brillouin zone. So if any point lies on this boundary, then that point on the Brillouin zone boundary lies on the perpendicular bisector between the point 0 and some reciprocal lattice point G. And you can very well understand it. If we connect this point to this point in reciprocal space and we draw the perpendicular bisector, then this will form the zone boundary of first Brillouin zone. Similarly, if there is a point present at perpendicular bisector to the right of this origin, then there will be necessarily points present on the on this side also. So Brillouin zone is kind of it represents the inversion symmetry also. It follows the inversion symmetry also. So this is what is said. Adding the vector minus g to this point necessarily results in a point which is on another Brillouin zone boundary on the bisector of the segment from 0 to minus g. This means that Brillouin zone boundaries occur in parallel pairs, symmetric around the point 0, which are separated by reciprocal lattice vector. So here G represents one reciprocal lattice vector whose length is equal to 2 pi over A. So if any point, if the points which are present on the Brillouin zone boundary this side, if they are translated to this side by subtracting this reciprocal vector, then we will reach another side of the zone boundary. Similarly, we can define another lattice vector because for this second Brillouin zone, and it can be defined as G is equal to 2 pi over A x cap plus y cap. Very important point is third, each Brillouin zone has exactly the same total area if we considering it a two-dimensional reciprocal lattice, or if we are considering the three-dimensional reciprocal lattice, then the volume of all the Brillouin zones is same. So for example, here the area of first Brillouin zone is same as the area of second Brillouin zone, and the area of second Brillouin zone is same as the area of third Brillouin zone, and so on and so forth. So for example, you can see how can you see? For example, if I translate this area by this reciprocal lattice vector, so this triangle will come here. It will come here. If we translate this region, it will come here. If we translate this region, it will come here. And if we translate this region, it will come here. So whole area of first Brillouin zone would be covered by the pieces of second Brillouin zone. Therefore, we can see that area or volume of all the Brillouin zones are same. Similarly, you can verify it if we translate these pieces of third Brillouin zone by this translation vector, then they will cover the whole area of first Brillouin zone. And fourth is also important. There are exactly as many K points or state within first Brillouin zone as there are unit cells in the entire system. This is again very important, and we will be going to use in our later discussions of lattice vibrations and other things. This fourth statement says that, for example, if we have n unit cells in the crystal, then there will be n K points in the first Brillouin zone. If there are 2n unit cells in the 2n unit cells in the crystal, then there will be 2n K points in the first Brillouin zone. Also, when we defined with the Brillouin zone, we also said that any wave whose wave vector starting from the origin terminates at the zone boundary, that will necessarily satisfy the diffraction condition. So that is the importance of Brillouin zone. Again, I repeat that any wave whose wave vector starting from the origin terminates at the zone boundary, that will satisfy the Bragg's reflection condition, and that can be easily proved. And today we are going to see it. So now, because we have assumed that in a crystalline solid, the atoms or molecules are arranged in a periodic fashion. If we go in any direction, then after a certain distance that defines the periodicity of that lattice or crystal, we will find the same type of atom and molecule. So crystals are periodic in nature, like the days of a week are periodic in nature. For example, today is Tuesday. After 7 days, again there will be Tuesday. After more 7 days, again we will have Tuesday. So this like this, we also have the periodic arrangement of atoms or molecules inside the crystal, and that is very important information that we can get this information about the periodicity of the atoms or molecules in the crystal by X-ray diffraction, and this is known as the crystal structure. To get the crystal structure information by studying the X-ray diffraction patterns. So crystal structure information about any crystal structure can be obtained by understanding the diffraction patterns of waves, and waves should be of appropriate wavelengths. So that is very important, and we are going to see why the waves should be of appropriate wavelength. We cannot use any wave. For example, we cannot use the visible light to study the crystalline structure of solids, and that incident wave of appropriate wavelength will interact with the solid, and it will produce a diffraction pattern that is the reciprocal lattice of this solid. So if when we shine X-rays on a solid, then it will get diffracted, and analysis of such diffraction patterns is our main goal. To analyze or to study such diffraction patterns is our main goal. It is common to study crystal structures using X-rays, we can study the crystal structure using X-rays, using neutrons, or using electrons. And you will be remembering that it was the Davison-Zermer experiment that proves uh, which proves that even these subatomic particles like electrons and neutrons, there is a wave associated with them, and uh, there is a wave associated with them. That's why they show particle as well as nature property. They exhibit the dual nature. All right. So we can use X-rays, we can use neutrons, we can use electrons to study the crystal structures. The results of crystal diffraction depend upon what is the crystal structure and what is the wavelength of the incident radiation. Suppose we are going to use the visible radiation or the radiation with wavelengths that lie in the visible radiation. Suppose we are going to choose 5,000 angstrom, then we cannot study, we cannot observe any diffraction pattern. It will just result in ordinary optical refraction from the solid. However, when the wavelength of the incident radiation is comparable to, or it is smaller than the lattice constant, diffraction will occur in directions quite different from the direction of incident radiation. So a little bit about what is the energy of the incident radiation, what is its momentum. We know that energy and momentum of a subatomic particle like electron or neutron, or be it photons, it is related, E is equal to hc over lambda, and its momentum is given by h upon lambda, where h is Planck's constant. Diffraction from crystal planes require that wavelength should be of the order of interplanar spacing d, or it should be either equal to d or it should be smaller than d. That we will see why this condition is required. And now you can see, when we are saying that the wavelength of the incident radiation must be of the order of interplanar spacing, that's why we cannot use the visible radiation to study the diffraction pattern of the solids, from the solids, sorry. So we have said that we can study the diffraction pattern using photons, but photons should be X-ray photons, not the visible photons, whose energy are of the order of kilo electron volt. Or we can use neutrons whose energy is 100th electron volts. And we can use electrons also whose energy is several hundred electron volts. This is the diagram that has been taken from the Kettle's book, and it again shows that for the similar wavelength, this is the, you see, this is the spacing, interplanar spacing between the planes in a solid. It varies from 1 to 10 angstrom. So if we want to study the crystal structure, then the wavelength of the incident radiation must also be of this order. And if the wavelength is of this order, then photon should have this much energy. These are X-ray photons. Neutrons should have the energy of this order. Electrons should have energy of this order. Only then they can exhibit the diffraction phenomenon. So for example, now we can calculate, we have X-ray and whose X-ray photon whose energy is given by hc upon lambda, or you can calculate lambda is equal to hc upon E. So if we consider an X-ray photon of wavelength 1 to 100 angstrom, then it will correspond to energy equal to 12 kilo electron volt. And this is what we are showing. We are seeing that If we want to study the crystal structure, then the energy of the incident X-ray photon should be in the kilo electron volt range. Only then it will correspond to wavelength which are of the order of interplanar spacing. Similarly, if we have electrons or incident electrons of wavelength, the same wavelength 1 angstrom, then we need to calculate what is the energy associated with them. So we can calculate energy should be 150 electron volt, and this is what we have said. We have said that energy should be of the order of hundreds of electron volt if it if these are the electrons which are incident on the solid. Similarly, for neutrons, for 1 angstrom wavelength neutron, the energy will be 0.08 electron volt. All right. So this is what we get. This is an X-ray diffraction pattern obtained from the powdered silicon samples, and you see we have several sharp peaks which denote the particular set of HKL planes. For example, this peak represents 311 HKL planes. So this means that these HKL planes 31111 represented by Miller indices 311, they have produced the X-ray diffraction when the incident X-ray beam was incident at an angle. By the way, this on the x-axis, this angle is 2 theta. This angle is 2 theta, and this is intensity. And it will be clear to you why we are plotting 2 theta, not theta. And this is very important question. In many interviews, it is asked why we plot 2 theta versus intensity. Why not intensity versus 2 theta? So you can calculate what is the angle of incidence here. It is 2 theta. So you divide it by 2. So that will give us theta. So what is the angle of incidence for the X-rays, so that the 311 planes will produce an X-ray diffraction? And this is the diagram again taken from the Kittel book. It shows that the X-rays are coming from the tube or from the X-ray source, and you know how we produce the X-rays. So these are the X-rays of all the wavelengths, and we have a monochromatic crystal. After that, what we will get? We will get X-rays of particular wavelength, and most of the X-rays will pass, only some part will go. And here we have a crystal that is kept on a rotating plate, and it will produce diffraction pattern, and the diffraction pattern will go in some particular direction, and it will produce this type of pattern. By beam diffraction takes place only in certain specific directions. As you have seen, we obtain these peaks only at particular angles, and in between them there is no intensity. The intensity is 0. So beam diffraction takes place only in certain specific directions, much as light is diffracted by grating. In optics, we study the diffraction of the visible light or the light of a particular wavelength using a grating. So similarly, the atoms which are arranged in a periodic fashion, they act like the lines on a grating. So they produce diffraction of X-rays. By measuring the directions of the diffraction and the corresponding intensities, information about the crystal structure responsible for the diffraction can be obtained. So it was the work of two father and son. One is Sir William Henry Bragg and his son William Lawrence Bragg. They were two English physicists, and they were working in the area of X-ray crystallography. So in 1913, when this son, William Lawrence Bragg, he was a graduate student at Cambridge University, and Professor William Henry Bragg was a professor there. So both of them developed a theory of X-ray diffraction. The first point of that theory is that if the atoms which are arranged in a periodic fashion in a solid, if these planes formed by these atoms, they act like a mirror. They act like a mirror, and if X-ray is incident on it, it will be reflected. Like when we have a mirror and light is incident on it, it is reflected following the Snell's law that says that the angle of incidence is equal to the angle of reflection. So they said that the father and son said that the planes reflect the X-rays in similar manner as a mirror reflect the visible radiation. So this is known as the specular reflection. And when we say specular reflection, so they said that specular reflection in case of atom is equivalent to diffraction. So diffraction is equal to reflection. So whether we use the term X-ray reflection or X-ray diffraction, both terms are same as far as the X-ray diffraction from the crystals is concerned. That was their one statement. And the other thing is they gave an equation that that will tell us how the diffraction is taking place. So the Bragg derivation, the derivation of Bragg equation is simple, but it is convincing since only it reproduces the results that agrees with observations. So these are the father and son, and you can verify who is father, who is son, and both of them got Nobel Prize in 1915. This is the only pair of father and son who got the Nobel Prize for working on the same problem. Though father and son or daughter or mother and daughter, many pairs are there who received Nobel Prize, but they were working on different problems. Here is the only example where father and son working on the same area, they received the Nobel Prize on the same problem in 1915 for their services in the analysis of crystal structure by means of X-rays. And when they received Nobel Prize, the son was fighting in World War I when he received the Nobel Prize. You see in what difficulty these scientists have worked. All right, and uh, we can people may think that okay, because father was already professor and he gave credit to his son also, so that son did not do anything, only father did everything and he gave name of his son. It is not like that. It was the son who worked more than his father. So the theory is reverse. So in a diffraction experiment, diffraction experiment, the spacing of lines on the grating can be found from the separation of the diffraction maximum. If we observe the diffraction of visible light from a grating, and we will see on the screen the maxima, minima, maxima, minima, maxima, minima like this, and the separation of these maxima and minimum by noting down these the distance between the maxima and maximum consecutive or successive maximas, we can calculate what is the spacing of lines on the grating. And also information about the structure of lines on the grating can be obtained by measuring the relative intensities of the different orders. Similarly, in the similar fashion, we can study from the X-ray diffraction maxima, measurement of the separation of the X-ray diffraction maxima from a crystal enables the determination of the unit cell size. Also, from the intensities of the diffracted beams, information can be obtained about the arrangement of atoms within the cell. So we have already said that we are going to use X-rays for study our solid in which the atoms are arranged in a periodic fashion. So, for example, this is a solid shown in which you can consider it to be like sodium chloride structure, in which the purple circles or spheres, they represent the chloride ion, and smaller green spheres, they represent the sodium ion. And this is the interplanar spacing, the distance between two atoms. It is known as the lattice constant, or we can consider any particular set of planes and we can calculate what is the interplanar spacing. So that if the wavelength of the incident radiation is of the order of this interplanar spacing or lattice constant, then it will produce a diffraction pattern. And we have already calculated what should be the energy. It should be in the kilo electron volt for the X-rays. All right. So we consider a crystal that is made of parallel planes. So this is a crystal in which you have the atoms arranged in a periodic fashion, and we can take any particular set of planes with interplanar spacing defined as D. Incident waves are reflected specularly. So specular reflection means it, it is a reflection as if a mirror is placed here. The wave is incident and it is reflected. So angle of incidence is equal to the angle of reflection. So in case of X-rays, X-ray diffraction from the solids, the diffraction is equal to the reflection. We have already discussed it. With each plane reflecting only a small fraction of the radiation, like a lightly silvered mirror. In a mirror-like reflection, the angle of incidence is equal to the angle of reflection. So this is the X-ray that is incident on this particular set of planes, and this ray is reflected in this direction, and this ray is reflected in this direction. But you notice here that this ray B travels more distance in the lattice in comparison to A wave. So now we are going to calculate how much extra length this B wave has traveled in comparison to this, and if this distance is equal to integer multiple of the wavelength of incident radiation, then there will be constructive interference. In the reflected between the reflected waves. If this distance is half integer multiple of this wavelength, then destructive interference will take, and we will observe zero intensity on the screen or detector. The diffracted beams are found to have maximum intensity when the reflections from the plane of atoms interfere constructively. I believe you remember the condition of constructive interference, in which the path difference traveled by the two waves must be integer multiple of the incident wavelength. And if it is multiple of half integer of wavelengths, then it will produce a destructive interference. We also assume that X-ray makes elastic scattering with the atoms so that energy of the X-ray does not change after reflection. So when X-rays strike a crystal, we want the condition for constructive interference between reflected rays from different planes. That is, we want the condition for the reflected X-rays to be in phase with one another they uh, so that they add together constructively. In this, the same diagram, two X-ray beams travel different distance. So for example, this A beams, it strikes this atom and it is reflected in this direction. This B beam strikes E atom, but if we draw the normals from C on this line, then DE plus EF, it represents the extra length, traveled by this second beam. Uh, it represents the extra length traveled by this beam. And if this is equal to integer multiple of the incident wavelength, then these two reflected waves will interfere constructively. Means uh, when this condition is satisfied, the maxima of this peak will be exactly at the same position where the maxima of this peak is, or minimum of these two peaks will coincide. They will they will interfere constructively, and we will get large amplitude. And since the intensity is proportional to the square of the amplitude, so we will get enhancement in the intensity. So you see the reflected angle is theta, the wavelength of the incident X-ray is lambda, and the angle between the incident X-ray and the reflected X-ray is 2 theta. So this angle is theta, and this angle is also theta. So the angle between incident X-ray and the reflected X-ray, it is 2 theta. That's why we plot 2 theta versus intensity in an X-ray diffraction pattern. So now we calculate this distance DE. We calculate, so this normal distance is equal to D. This normal distance is equal to D. If this angle is theta, this angle is also theta. And if this angle is theta, this angle is 90 degree, DE would be equal to D sine theta. Similarly, EF would be equal to D sine theta, and we add them, DE plus EF, that would be equal to 2D sine theta. And we said that constructive interference will take place if this extra distance traveled by this second beam is equal to integral multiple of the wavelength, that is equal to n lambda. So whether the path difference is 1 lambda, 2 lambda, 3 lambda, 4 lambda, all these waves here, all these reflected waves will necessarily interfere constructively, and they will produce uh, an intense spot on the detector. So that is 2D sine theta is equal to n lambda. It is known as the Bragg's reflection condition, or Bragg's diffraction condition, or Bragg's law. Now you see here the maximum value of theta, sine theta. Sine theta can vary between 0 and 1, and it can be maximum value of theta can be, sine theta can be 1. Sine theta can never be greater than 1. So if we put sine theta equal to 1 here, n lambda will be equal to 2D. So this proves that the wavelength of the incident radiation should be either equal to the interplanetary spacing, or it should be smaller than the interplanetary spacing. If it is greater than, much greater than the interplanetary spacing, the Bragg's law will not be satisfied and we will not observe the diffraction pattern. Again, this is the diffraction of X-rays from only one plane, and you can see that the two X-rays are incident. One is reflected from atom A and the other one is reflected from atom B. The two will interfere constructively if the distance traveled uh, by the upper wave, that is equal to dB, is equal to the distance traveled uh, by this wave, that is equal to AC. So if AC and dB are equal, they will produce constructive interference. But as I have told you, only part of the incident wave is reflected. So the reflection or the intensity from a single plane, that is very, very less. In order to observe very large intensity after constructive interference, we require several planes. We require reflection or diffraction from several planes. So I the why this is so, each plane reflects only 10 to the power minus 3 to 10 to the power minus 5 of the incident radiation. It is not a perfect reflector. This means that we require 10 to the power 3 to 10 to the power 5 planes, so large number of planes, to observe, to contribute to the formation of Bragg reflected beam in a perfect crystal. So I told you about the Bragg's law and about the father-son work, and they did this work in 1913 and they got Nobel Prize in 1914. Another German physicist named Max von Laue, he was also working on these diffraction patterns from X-rays, but in a different manner, and he developed a method also that is known as Laue method, and that would be part of your fifth assignment that I will give you today. So he was born as Max Lowe, and but his father, because they were Christians, and his father was given some title in church, that is von. So later they added von. It represents some religious term in Christianity. So we don't call it the Laue pattern or Laue condition or Laue formulation. We call it only Laue formulation, not von Laue formulation. This von represents something related to Christianity. The interesting thing about about this Max von Laue is that he was a German physicist, but he was a Jew, like all other famous scientists like Einstein and all that. So Max von Laue won Nobel Prize in 1914 for his work in the field of crystallography. And I'm going to tell you a very interesting story. So because he was Jews, and during the reign of Hitler, there were massacres of Jews by Nazis in Germany. So what he did was, the gold medal which he received in Nobel Prize, Max von Laue, he sent his gold medal to the Niels Bohr Institute in Denmark to save it from the Nazis. And it was, at that time, it was a crime to send gold from Germany, outside Germany. If the German government or the Hitler government at that time could have known that Max von Laue had sent his gold medal to some other country, he would have been jailed. So then there was Second World War broke, and the Nazi or the German army attacked the Niels Bohr Institute and they captured it. But there was another chemistry Nobel laureate with whom this gold medal was kept, and he was working on the aqua regia solution. I believe you understand about the aqua regia solution. That is 3 part of HCl and 1 part of HNO3. That forms the aqua regia solution. So when that chemistry Nobel laureate, I think he was Harvesi or something like that. So he dissolved this gold medal in that aqua regia solution. So now it becomes solution, and it was kept on the on one table. The Nazi army attacked the Niels Bohr Institute. They captured it, but they found on the table, okay, one particular solution is kept there, nothing is there. So they left it. After that, when World War finished, the same solution was found there, and again the gold medal was recovered from it, and the Nobel committee that gives these Nobel medals, they again formed the same medal from the same gold that was dissolved in aqua regia solution, and they again presented this Nobel laureate medal to Max von Laue. Isn't it the interesting story?
Yes, sir.
So now we have seen that the wavelength of the incident radiation must be equal to or smaller than the interplanetary spacings or the lattice constant of the unit cell. So this is before we want to study how, because in the Bragg's law we have verified that this is the diffraction condition, but we don't know about how this X-ray is interacting with atoms, how this X-ray is interacting with electrons and like that. So that thing we will study now. And before studying that, we would like to study about the Fourier analysis of a periodic function. We are saying that in a crystal, atoms are arranged in a periodic fashion. So for example, you see this is the one-dimensional model. It is just a model. The yellow circles represent the atoms, and after a certain distance, you see the yellow circles, and that is the periodicity of this one-dimensional crystal. And many things are periodic, since, for example, if we consider the electron concentration, whatever is the electron concentration here, the same electron concentration is here, the same electron concentration is here. So electron concentration is also periodic in nature. If we have the magnetic atoms present here, their magnetic moment is also periodic in nature. If we have electrons, there are charge associated with them. So that charge, or charge density is also periodic in nature. So many physical properties are periodic in nature. And if we have any periodic function, it can be represented by a Fourier transformation, by a series that consists of terms in cosines and sines. The physical process leading to X-ray scattering is the electromagnetic field of the X-rays that forces the electrons in the material to oscillate with the same frequency as that of the field. These oscillating electrons that emit new X-rays that give rise to an interference pattern. So like I have told you that if you consider charge concentration, if you consider the electron number density, or if you consider magnetic moment, all these properties inside a crystal are periodic in nature. This means that they will remain invariant under a translation operation defined by this vector T, that is equal to N1A1 plus N2A2 plus N3A3, where N1, N2, N3 are integers and A1, A2, A3 are primitive vectors. So what do we mean by translationally invariant? If we are, for example, we are measuring the electron number density n at a position vector r, it should be same at position r plus t. In one dimensional case, it would be nx should be equal to nx plus a, or it should be equal to nx plus ma, where m is integer. So whatever is the electron density I see here, if I translate it by, let's say, I move by 4a, the same should be visible, the same should be seen here. Then we say the electron, what we say, electron number density is translationally invariant. Such periodicity creates an ideal situation for Fourier analysis. So electron number density nr, n at position r. So electron number density means number of electrons per unit volume. That's why it is represented by small n. N at position r can be expressed as a special Fourier series expansion. I believe you have studied the Fourier analysis. So one is in the time and frequency domain, and the other one is in the space. So because we are considering this electron number density in space, so it can be expressed spatially as a Fourier series expansion. The most interesting properties of crystals are directly related to the Fourier components of the electron density. This electron density, or the charge density, as we would see later, is very important in case of X-ray diffraction patterns. First, we consider one-dimensional case. So electron number density at any position x is defined by n of x, and it is the lattice or crystal has a periodicity of a. So we expand nx in a Fourier series of sines and cosines, and you see n of x can be written as summation p equal to 0 to infinity, and this term containing cosines and this term containing sines. So if we put p is equal to 0, we will get this first term, because it is a constant, it can be taken out, and then summation will run from p greater than 0 to infinity cp cos 2 pi p x upon a plus sp sine 2 pi px upon a. आप लोगों ने ये पढ़ा है ना फूरियर सीरीज? ऐसा किसी भी फंक्शन को हम ऐसे लिख सकते हैं, कोई बताए मुझे?
Yes, sir.
हाँ, क्योंकि ये कोई नई चीज नहीं है, पढ़ा होगा तो आपने. हाँ, तो यहाँ here we are considering p as positive integers. P is greater than 0 up to infinity, and cp and sp are real constants. These are known as the Fourier coefficients of the expansion. But you see here we are restricting, if we represent the any periodic function in this form, we are considering, or we are restricting ourselves to only positive numbers of p. But later on in coming slides, we will see that if we can define this in terms of exponential, the periodic function in terms of exponential, that then we can include the negative integer value of p also. So since we have this factor in the argument 2 pi over a, 2 pi over a. So this ensures that nx is translationally invariant. So we can see if we write it nx plus a, that should be equal to n naught plus summation cp cos 2 pi px upon a plus 2 pi p plus summation sp sine 2 pi px upon a plus 2 pi p. And you see 2 pi multiplied by n integer, and the cos of that 2 pi p again is 1. So whether you take cos 2 pi, cos 4 pi, cos 6 pi, this is equal to 1. So this term would give us 1. So again we will get n naught plus summation cp cos 2 pi px upon a plus sp sine 2 pi px upon a is equal to nx. So this proves that this number density in one dimensional, when we define it by this Fourier expansion, it remains translationally invariant. And this term in the argument, if you recall it, if we have a lattice with lattice constant a, we can make a reciprocal lattice from it with the reciprocal vector as given by 2 pi over a, 2 pi over a. So if any lattice is periodic with periodicity equal to a, its reciprocal is also periodic with the periodicity of 2 pi over a. And this 2 pi over a multiplied with this integer will give different reciprocal lattice vectors. So we say that this 2 pi p over a is a point in the reciprocal lattice or Fourier space of the crystal. In one dimension, these points lie on a line. The reciprocal lattice points tell us allowed terms in the Fourier series. So all the points you see in the reciprocal space, they are the allowed Fourier terms. They are the allowed Fourier terms. A term is allowed if it is consistent with the periodicity of the crystal. As this I have already told you, a system periodic in real space with the periodicity of A will be periodic in reciprocal lattice with a periodicity of 2 pi over A. So for example, this will make things more clear. We have something that is periodic in nature. So you see, maybe you can consider this to be one unit cell or one primitive cell, one unit cell, you can consider this. And if you repeat it, this will form the one-dimensional lattice. So here periodicity is A with units as meter. So this is number density. This is the electron number density. This is how it is varying some function. Again, it is taken from Kittel. So in the reciprocal space, this we will define as this to this distance is 2 pi over a. It will be all the reciprocal points can be defined by this 2 pi p over a. Second point will be 2 into 2 pi over a, that is 4 pi over a, 6 pi over a, 8 pi over a, and in this minus 2 pi over a, minus 4 pi over a. And it is k-axis. It is momentum space, reciprocal space, Fourier space, whatever you call it. Only these points are allowed because these are the solutions of Fourier expansion. No solution exists in between the 2 points. And its unit is, because it is inverse of A, so its unit is meter inverse. So I told you that when we define any periodic function by this way, we are considering only the positive integers. But if we define the same function, and both of these expressions are same, by this equation where summation p np exponential I 2 pi p x upon a. So this p will have all positive, negative, and zero value. So this is more convenient, more simpler, and because it has been expressed in terms of exponential, and dealing with exponential is simpler. So this is more usable form in place of this equation. All right. The coefficient here np are complex number. These are complex number. But remember, our electron number density, because electron is real, it is in real space, their number density is also real. And here we are saying this is exponential, this is this is complex, this is complex. So we should prove that whatever term we are going to take here, ultimately we are going to get a real electron density. It should be real, it should not be complex number. So but here we are saying the np's are the coefficient, the Fourier coefficient np's are complex numbers. And in order to ensure that this is a real number, this condition must be satisfied, that np must be equal to the complex conjugate of n minus p, the complex conjugate of minus np. So np, we can verify it. Np, we are saying it is a complex number. So let's say it is equal to e to the power iy. Let's say np is equal to e to the power iy. When we take n minus p, so it would be equal to e to the power minus ipy. np is equal to e to the power ipy. N minus p would be equal to e to the power minus ipy. And when we take its complex conjugate, again it will become e to the power ipy. So this condition should be satisfied. That will ensure that this is a real function. So now in this equation, we let phi is equal to 2 pi px upon a, and we expand this in terms of p and minus p. So it will become, so np, when e to the power I phi, it will become, so I phi is cos phi plus I sin phi, and when we put minus p, so we will have n minus p cos phi minus I sin phi. These terms can be reshuffled, cos phi terms can be taken together, np plus n minus p cos phi plus iota np minus n minus p sin phi. And np, remember, is a complex number. So it is equal to e to the power ipy, and it would be equal to e to the power minus ipy. When you add these two terms, so their real parts will come, and their imaginary part will cancel out. In this, their real part will cancel out and their imaginary part will come. So here I is already there, and you will have another imaginary part. So I and I will become I square, and I square will give us minus. So this will become, this is real, this is real, this is real, this is real. So nx will become real. So this expression can be written as 2 real np cos phi minus 2, because here you will have only the imaginary part. So 2 minus imaginary np sin phi. Here real part of np and imaginary part of np are real and denote the real and imaginary part of np. Thus we see that this nx is a real function. This nx is not a complex function, but it comes out to be a real function. So this what we have done so far is, it is in one-dimensional space. We can extend it for three-dimensional case, and in that case we need to consider n as a function of position vector r. So n are in that case would be given by summation g ng exponential to the power I g dot r. So this g represents the reciprocal vectors, and it should remain invariant under this translation operation T. So that we can prove n r plus T should be equal to, if we in place of r we replace r plus T, so n r plus T would be equal to summation g ng exponential to the power I g dot r and exponential to the power I g dot T. If you recall the previous lecture, in that lecture we proved this relation, and I told you that time that we are going to use, so exponential to the power I g dot T, it is equal to 1. So here you put equal to 1, and what you get is nr. So electron number density in three-dimensional case also we have proved that it remains invariant under this translation operation. And we shall see that this coefficient Ng determines the X-ray scattering amplitude, whether we take electron number density or we take the electron charge density. Both are the same thing, because here I am using different notation and later I will be using different rotation where this is represented by rho g. So that you can call electron number density or the electron charge density. But this coefficient will determine the X-ray scattering amplitude. Now, in order to calculate this NP in this equation, where it is, so we can calculate this NP. If we multiply this equation by e to the power minus I 2 pi px upon a and integrate it, we can calculate NP, and this is how it is given. The NP is equal to a to the power minus 1, 0 to a dx nx e to the power minus I 2 pi px. Both sides we have multiplied by this and integrate the term between 0 to a. So this is how we are going to get NP, and now we have nx. Nx can be replaced from this expression. So for NP we are going to get this term, and because we are already having P, so we need to have different P for this series. So P prime, we can represent P prime. So summation is from P prime and P prime dx exponential I 2 pi P prime minus P x upon a. Now, if P prime is not equal to P, the value of integral is, it is the exponential e to the integral of e to the power I some integer times x. You know how it is calculated. So it will give us a upon I 2 pi P prime minus P e to the power I 2 pi P minus P minus 1, and that would be equal to 0, because P this is also integer, P prime is integer, P is also integer, their difference will also be integer, and e to the power I 2 pi multiply some integer is again always 1. So 1 minus 1 would be equal to 0. So if P prime is not equal to P, the result would be equal to 0. The result would be equal to 0. That's why we are not going to get any solution in between the lattice points. However, if P prime is equal to P, the integrand here is P prime is equal to P, it would be equal to exponential to the power iota 0, that would be equal to 1, and the value of integral would be to the power iota a, and it would give us a. so that NP would be equal to A inverse NP, A is equal to NP. And similarly, we can see that inversion of what would be the value of Ng in 3 dimension. This we have calculated for NP. Similarly, we can calculate for Ng. Ng here we have defined. Ng would come out to be this. So now we are going to study, we are going to incident X-rays. We are going to incident, just a minute, pigeon has entered my room. I need to do something. Yes. So when we study about the Bragg's law, that is only in the necessary condition, but not the sufficient condition for the diffraction. And using the X-ray diffraction, we can study about the structure factor and atomic form factor. These are the two things. Atomic form factor will define, will tell us about the scattering of X-rays or the reflection of X-rays from the individual atoms. And when we say structure factor, that will define us how in a unit cell or what in a unit cell different atoms or similar atoms are present, what is the contribution of that particular unit cell to the X-ray scattering. So for this purpose, we do this experiment. We take an X-ray source and it is a point source. So it is generating X-rays in all the directions, and these X-rays are spherical in nature because the source is the point X-ray. I encourage you to once again recall how X-rays are produced. So this is a point source and it is producing X-rays in all the directions. These are spherical waves, but when these spherical waves travel a long distance, so they can become the plane waves. They can, so this will be larger, this will be larger. So at larger distances, they can become like the plane waves. So we know what is the plane wave equation. E is equal to E naught e to the power I k naught dot r minus omega t. Here E naught represents the amplitude of X-ray at this source, and K naught represents the wave vector that is related to the wavelength of incident radiation as follows: 2 pi over lambda. This is how its magnitude is given. K naught is equal to 2 pi over lambda. So here we have a crystal, and this is some origin. This is the some point in the crystal, the O, and it represents the origin. We take the point from where the X-rays are scattered in this direction, and at point P we have the X-ray detector. Again, these plane waves, when they oscillate the electrons here, and these electrons again oscillate with the same frequency of the incident radiation, and they produce X-rays in all the directions. And again, these are spherical waves. These are again spherical waves. They are moving in all the directions, and we are at any instant, the detector is here, which is moving like this, So it can capture all the scattered X-rays. It can capture all the scattered X-rays. So now we define some mathematical terms. The distance between the X-ray source to this point origin is denoted by vector capital R. Since this point is taken as R, so this distance is capital R plus R. From the origin, the X-ray detector is R at a distance R prime vector. And since this is R, so point P, this distance is given by difference of R prime vector with R. Now, because we are not dealing in time, we are not considering at this time X-ray is here, at that time X-ray is here. We are dealing with spatial part only. So for the time being, we can neglect this time component or the phase part here, but we are assuming it is present, but we are not showing here. So we are considering only the spatial part of this equation. So this equation will become E is equal to E naught e to the power iota k naught dot R. So this is the X-ray source. This is incident on the crystal. We take a point that acts as a scatterer. So there are many scatterer in this crystal present. Scatterer may be electron, scatterer may be atoms. So many scatterer are present, and we consider only one scatterer that is located at our vector position with respect to origin, and then this scatter again emits X-rays, and they are spherical in nature. And these are the plane waves for which we have written this equation. The incident wave induces the emission of spherical waves in all the direction at all points R of the target material of the crystal. Again, the same thing. So here E naught represents the amplitude of oscillation of electric field at the X-ray source. The incident wave has wave vector denoted by K naught. The outgoing wave or the scattered wave or the reflected wave has wave vector denoted by K. In some of the books, you will find that the incident wave vector is denoted by K and the scattered wave vector is denoted by K prime. And since these are the spherical waves, and these are reaching at the detector, which is not too far from this crystal. So that's why these spherical waves will remain spherical. They will not become parallel plane waves. They will remain spherical when they reach the detector. So now we want to see what is the scattering wave contribution from P that are reaching at point B. So the electric field at point B is proportional to what is the electric field at point P, what is the density of the scatterer at point P. So this is like this, and since they are spherical waves, they are moving in this direction, and you know that spherical waves are given like this when we have 1 upon R in the equation. So that represents the spherical wave. So amplitude or magnitude of electric field of X-rays reaching at point P after scattering from the scatterer at point P, their electric field is proportional to what is the electric field at point P, what is the density of scatterer at point P. So you can write, and this will also have this kind of term, e to the power I k dot this distance r prime minus r. So what is the electric field at point P? This is E naught to the power E I k naught times this distance. This has traveled this distance r plus r. So we put the expression for EP, E naught e to the power I k naught dot r plus r divided by r prime minus r rho r e to the power I k dot r prime minus r. And one thing we assume that this distance is the distance between scatterer at P and the detector is large in comparison to this distance. So it is much greater. So in place of r minus r, we can write only r prime, and we can reshuffle the terms k naught, or in terms of capital R or r prime we can take together, and in terms of small r we can take terms together. This is the electric field. This is the electric field that at point P of the X-rays that are scattered from the point P. Now in a detector, it measures the intensity. And we know that intensity is the square of the amplitude, and we have calculated the amplitude here. If we square it, then we will calculate the intensity of the X-rays that are scattered from the point P. But we are interested, what is the intensity of X-rays that is scattered from the whole crystal, So in that case, we need to integrate this over whole volume of the crystal. So square is because it is the amplitude square that will give intensity, and integral here is over the whole crystal. So because E naught is constant and this r prime is also constant, the distance between the detector and the crystal is same, so they can be taken out of the integral, and this is also a constant. It can also be taken out of the integral, and they can form the proportionality constant. They can be brought inside the proportionality constant, this term and this term. So they have been absorbed in the proportionality constant. So we will get this equation. Here you see the difference in the wave vector of the incident X-ray and the scattered X-ray, that is k minus k naught. K minus k naught. We denote it by some another vector, that is kappa. So kappa represents the difference between the wave vector of the incident X-ray and the scattered X-ray, and this is known as the scattering vector. Somewhere it is written as delta kappa, and it is denoted by incident is denoted by k, and the scattered is denoted by k prime, and incident is denoted by k. So that is just a use of different notation. So here you have the terms rho r, that is a periodic function, that is periodic in nature, and you can see that we can represent any periodic function by Fourier expansion. So diffraction intensity is the square of Fourier transformation of the scatterer density, that is rho r. Since rho r is periodic in nature, so it can be represented in one dimension by this Fourier series expansion. And this is the same thing I have. You can see it, just no discussion, we have already discussed it. All right, I think I should break it. I should stop here because it is time, and we continue in the next class, and I will give you assignment. The topic I will mail you. And if you have any questions, please ask questions. No, if you are shy asking question here, you can write to me. So with this, let me conclude the lecture. Let me stop the video.